Class, today we're on lesson number 3 and chapter 10 of factoring, and we're going to be dealing with polynomials and their factors. So we've already understood how to factor out numbers. We touched into monomials in the second lesson and their properties and how we can factor those things. And now we're going to expand it into polynomials. And you're going to see that we are going to apply some of the basic principles that we learned, particularly like the distributive rule. We have to look for factors within different terms and factor them out. So let's take a look here. Let's read on page 455. Emmanuel Zacchini holds the world record for traveling the longest distance through air after being shot from a cannon. This photograph shows him with his daughter Florinda performing their act at the circus. Now, the distance of a human cannonball above the ground depends on the time that has passed since he or she was shot upward. For someone who leaves the cannon with an upward speed of 64 feet per second, the distance is given in feet by the polynomial 64x minus 16x squared. So let's write this polynomial here. We have 64x minus 16x squared. Now this represents, again, this is the distance given in feet if they are shot. If someone leaves, for someone who leaves the cannon at an upward speed of 64 feet per second, so they're going to be traveling 64 feet per second, in which now x represents the number of seconds that have passed. So let's just pause for a second and take a look. As we increase numbers here, this number is going to increase, right? So as x increases. Now notice what happens here though. As x increases, x is going to be squared, then multiplied by 16. So you know that when you start squaring a number, it starts getting larger faster, okay? If you put in 1, you'll have 64 times 1, and you would have 1 squared times 16. But imagine when you get to, let's say, the number 4, you would simply have 4 times 64, right? But you would have 4 squared and then times 16. So you can see that the squaring, and we understand that the exponential growth, that's a factor that's going to happen on the right side over here. But let's continue reading at the top of page 456. Evaluating this polynomial for different values of x. We can see here, and we've done this before with creating tables, we have 0. So if we put in 0, the value is going to be 0 times 64 minus 0 squared, which is 0 times 16. So it's 0 minus 0. So at 0 seconds, there is no movement, obviously. But as we continue to move, we can see that we have, after 1 second, 48. Okay, so for this table, we see that 1 second, the distance above the ground is 48 feet. After 2 seconds, it is 64 feet. Then, after 3 seconds, it is 48 feet. So we can see what's happening here is that when we multiply 3 times 64, we have 3 being squared, which is now going to become 9, and 9 times 16, and when we subtract these two, the number is 48, which basically means that he's coming down, he or she, because they were at 48 after the first second, 64. Okay, so if we were just take a look, if this were the ground, you know, and this is not a graph, I'm just showing you, in a sense, the height. Okay, I'm just going to put the person's height here, and then their height is going to be here, and then their height is now here. Okay, so they started here. Now of course we can do this as a graph, but I'm not drawing the graph right now. So we're just looking at this in relationship to the ground. Okay, that's the distance above the ground. So after 4 seconds, it's the height is 0, so you're right back to the ground. So you can see they went up and came back down. Now, the trip evidently lasts 4 seconds. There's a way to tell how long the trip would take without bothering to make the table of values as we have done. Now, isn't that a wonderful thing? I always tell you we learn things the hard way, and then we show you a little bit of a shortcut, okay? Now, the method works like this. Clearly, at the beginning and the end of the trip, the distance of the human cannonball above the ground is 0. This means that at these times, the value of 64x minus 16x squared is 0. The values of x that will make a polynomial in x equal to 0 are not usually obvious. However, in this case, we can perform a few operations that will let us see exactly which values of x will make it equal to 0. Now notice that the two terms 64x and 16x squared have a common factor of 16x. Now we would have known that when we factor, we know that we have factors here, a common factor, the greatest common factor of the coefficient here. When I'm looking at 64 and 16, I'm thinking, yeah, that's 16, right? Why? Because over here we have 4 times 16, and over here I have 16, right? 4 times 16 times x. And on this side I have 16, obviously, times x times x. So I have a 16, so I have two 16s, and I have, well, two x's, one of each, on each side. So we can say that the greatest common factor, okay, is 16x. Now factoring 16x from each term and applying to the distributive rule relating multiplication and subtraction in reverse, we can then write it this way. We can factor this out and say 16x times, well, what's left over? I have 4, right? And what's left over on this side? Because I already used the 16, I used the x, I used the 16, I use the x, so the other is minus, because this is being subtracted, and we're left with the x. So we can rewrite this polynomial to look like this in terms of factoring out, showing it as the distributive rule would show us in factoring. We have 16x times parentheses 4 minus x and parentheses, so that would be 16x times 4. Okay, we know it's 64x. 16x times x, we know it's 16x squared. Okay, make sure you have the minus sign. Now, knowing this, let's take a look. It says we have written 64x squared minus 16x squared as the product of 16x and 4 minus x. We know that a product is 0 if one of its factors is 0. Okay, so the product 16x times parentheses 4 minus x and parentheses is 0 if either x or 4 minus x is 0. So we know we're multiplying. Okay, we're multiplying. There's a big multiplication dot right in the middle. It's really big. But we know that if this is 0 on this side, then it doesn't matter what you multiply what's here, it's going to equal to 0. And again, if we can make this side equal to 0, then it doesn't matter what's on this side, because again, we're multiplying, so anything times 0 is equal to 0. So in the first case, we know that if x is 0, okay, if we had 16 times 0 times, let me just put my parentheses, 4 minus x, what will we have? Well, 16 times 0 is equal to 0, and I multiply that times 4 minus x. Doesn't matter what's going on in here. Of course, I'm sorry, I should have written a 0 in there for the x, because we are substituting the value 0. Okay, so let's do that. So we have 16 times 0 is 0, and 4 minus 0 is 4, but 0 times 4 is equal to 0, so we know that if x is equal to 0, then this will be 0. Also, if we take a look at the other side, we say 16x and 4 minus x. Now, if we make this side 0, and how can we do that? Well, 4 minus 4 would be 0. So let's make x 4. Okay, so we have 4 minus 4. And again, we could have spotted this quite simply just looking at it, saying, oh, over here x needs to be 0. Okay, we have that one. Over here x needs to be 4. Okay, if x is equal to 4, then what do we have? Well, this is going to be 16 times 4 times 0, and it doesn't matter what you're multiplying. If you're multiplying everything by 0, the answer is going to be 0. So that one works as well. So when x is equal to 0 or 4, then the human cannonball is 0 feet above the ground. At the beginning of the trip, 0 seconds, and at the end, at 4 seconds. This is just one example of why it is useful to be able to rewrite a polynomial as a product. In lessons 1 and 2, we learned how to factor integers and monomials. In this lesson, and the following ones in this chapter, we will learn how to factor polynomials in general. Throughout our work, we will restrict factors to integers and polynomials having coefficients and constant terms that are integers. Okay, it can get much more complex when we're dealing with fractions, but right now we're focusing on integers so that you learn these basic principles, these concepts on how to factor out a polynomial. So let's take a look at this example. Get a new board here. All right, get my pencil back, and let's take a look here. We have factor 5x squared plus 10x. Okay, so let's do that. We have 5x squared plus 10x. And illustrate the result by means of the area of a rectangle. Okay, so we're going to draw a little box over here. All right, well, let's not draw the box yet, but we can illustrate it afterward. So we don't really know how many factors are going to go inside, though I could pretty much see it clearly. Now, we have to determine the greatest common factor. So the first thing we deal with the coefficients, and we know that this is 5, and we know this is x times x. Okay, let's just write that out. And over here, we know that we can factor out a 5 as well. We know the greatest factor here is 5. Okay, and again, we're limiting ourselves to integers, because I could easily say 1/2 times 10, and that would be a factor, right? 10 times 1/2 would be 5. But because we're limiting ourselves to integers, we're going to focus primarily on that. And let's take a look on this side. We have 5 times 2, right? 5 times 2 is 10, and that would be times x. Okay, so what do we have? Well, I can take out the 5, right? There's a 5 on each. I can take out an x, and that's pretty much it, right? All right, so 5x would be our factor that we're going to factor out. Now, what are we left with? Well, we are left with x. This is being added, so we add a plus, and there's a 2 on this side because we've already used these factors, 5x and 5x. Okay, so we're left with an x and we're left with a 2, so that will be x plus 2. So if we take a look, we've rewritten this polynomial as a factor of really we can represent this as the distributive rule, as we have said before, 5x times parentheses x plus 2. So we have two factors here, really. And when we factor, we should end up with two factors. And what makes it a factor is that we're multiplying 5x times x plus 2. Now you might say, well, there's a binomial here, and there is. But ultimately, we still have a factor here. Over here, we don't. This is a polynomial all on its own. And we've gone over the descriptions and the definitions of what a polynomial is in Chapter 9. But this is not a polynomial. We can express this as a polynomial as we have it here. But we're factoring, and it's sort of like reversing it out, trying to determine what these factors are. Now, if we were to express this in the area of a rectangle, it would look as they have in our text. And what do we have? Well, we would have 5x here. Okay, we'd have two boxes because we only have two terms. We have one term on one side and two terms, so we'd put the x and we put the 2 here, right? And if we notice we multiply x times 5x, what do we have? 5x squared. And 5x times 2, that would be 10x. And that takes us right back to our original polynomial, 5x squared plus 10x. Okay, now we have another example here. And let's go ahead and write factor x to the 4th power. So let's take a look at that. We have x to the 4th power minus 2x to the 3rd power plus 2x squared. Okay, again, we're looking for the greatest common factor, and that would be the greatest common in each of these three terms. What are our three terms right now? We have x to the fourth power, we have negative 2x cubed, and we have positive 2x squared. So we know that there are x's in each one. That's the first thing I'm looking for. I says, okay, great, we have some x's in here. We also have some coefficients, but one of the coefficients is 1, so the greatest common factor in the first one is going to be 1, so I'm not even going to bother looking at the coefficients here because I really cannot factor anything other than 1. And of course, we wouldn't just factor out 1. So we're kind of left to not factor anything in terms of the coefficients. Now, had this been a 2 or a 4 or a 10 or any even number, I would have had a great opportunity to pull out the 2 as well, but we don't. So what do we have here? Now let's take a look. I like to go to the smallest power because at that point I know that I have an x squared here. Okay, that's going to be the greatest factor that I can pull out of x in this side. So looking at this, I know I have an x squared here times x, right? I have, all right, negative 2 times x squared times x. That'll give me x to the third. Okay, so I have over here, let me write my 2 times. I'm just going to use that times in there so we can start separating these factors and you can see them a little clearer. Okay, so we're looking at the x squared term. And again, I'm working backwards. It's easier to look back here and say, well, this is the one that I'm going to try to factor out all of these. So what do we have here? Well, we have x squared times x squared, right? Because we would add the two exponents, that will give us x to the fourth power. So now that we've begun to pull these apart, we can see that common factor is x squared in all three. And it's easy. All we have to do is put x squared out here and then just write everything else that's left over. Well, we had an x squared. Okay, so I already used this. I wouldn't write this on you. It's nice to keep your paper nice and neat, but I'm just kind of showing you what my mind is doing. I'm just getting rid of that x squared, and I'm left with x squared. Okay, and again, it wouldn't hurt if you had to scratch it out just to keep an order and keep your work organized. But you know, I don't recommend that you erase or remove things because sometimes you have to go back and take a look at your work and see, well, I made a mistake and I need to see what I did. So we're going to factor out this x squared here. That's going to leave us with a negative, or it's minus, and there's a 2, right? Because I'm getting rid of that. So there's a 2. And there's an x left over, and over here it's plus, and I'm left simply with the 2, okay, and parentheses. So I would have x squared times the parentheses x squared minus 2x plus 2 and parentheses. So this would be our answer if we were to factor. Now, just going back, let's take a look at what we're being told to do. We need to understand what instructions are. In example number 1 and example number 2, what did they tell us? They told us to factor, okay? And when we are told factor, okay, we should have something times something, okay? What those two are, well, it obviously depends on what we're given. Okay, if we're told to say factor 10, we could say 5 times 2. Okay, obviously we can show all the factors. We can put 10 times 1, 5 times 2. But when we're dealing with polynomials, we're going to have to look for the common factors because there are terms. Remember, polynomials are being added. You have monomials that are being added and subtracted, so we have to find the greatest common factor. Okay, now let's continue reading here at the bottom of page 457. Because we're restricting the factors of polynomials to integers and polynomials that have integer coefficients, some polynomials cannot be written as products of polynomials of a smaller degree. Again, let's emphasize, because we're restricting the factors to integers, because we can play around with fractions and decimals. You can go infinitely into those. Positive integers that cannot be written as products of smaller positive integers are called prime. We will define prime polynomials in the same way. A prime polynomial is a polynomial that cannot be written as a product of polynomials of lower degree. So let's just say, I'll give you a quick example here before we turn the page, but let's say we had the same problem, Okay, and I get my pencil back. Let's say we had this problem of x squared, or x to the fourth, minus 2x cubed plus 2. Okay, now what did I do? Well, I took out the x squared here. So the question is, are there any common factors? And we wouldn't find any. We would not find any. We'd say, well, there isn't one. So that means that this is a prime polynomial. There's nothing I can do here because there is no factor that I can find in each of these 1, 2, 3 terms that are common. Okay? So now it doesn't necessarily have to be an x. If this were a 2 here, I'd be able to factor out a 2, right? Or if it were any even number, I'd factor out a 2. But there isn't. And there are x's here and x's there, and, well, there are no x's over here. So we have a prime polynomial. Okay? Now, a polynomial, like an integer, can be written as a product of prime factors in essentially only one way. Let's turn over a page to 458 and take a look. We have here factor 6x minus 24 into prime factors. Now, we're being told prime factors. So we got to remember what prime factors are. And let's read here. We have the greatest common factor of 6x and 24 is 6, right? Because if we looked at 6x minus 24, well, there's no x here, so there's no x factor to be common. But we know we have a 6, and this would be 6 times 4, right? 6 times 4, so we have 6 times x. And so that means we can factor out a 6. We can actually write this as 6 times x minus 4, right? Because we're factoring out these x's and we're left with x minus 4. Okay, now factoring 6 into primes, we get 2 times 3. Can x minus 4 be factored? If so, it can be written as a product of polynomials of lower degree. Because x minus 4 is of the first degree, its factors would have to be of 0 degree. But polynomials of 0 degrees are constants, and the product of constants cannot be equal to x minus 4. So x minus 4 is prime. Okay, we cannot factor this anymore, is basically what they're saying. So we can write this now as 2 times 3 times, I'm just going to put that out there. You don't really need it, but I'm just kind of showing some separation here. Okay, x minus 4. We were told to factor 6x minus 24 into prime factors. So we have 3 prime factors, right? We have 2 times 3 times x minus 4. Okay, now there could have been an example where we could have, let's say this were x squared, right? And let's say this was x, all right? Just kind of giving you an example, and we're going to work over on this side. We could have factored out the 6, right? We would have said, oh, 6 times x squared minus 4x, right? That's what we would have had. And we could have factored this as 2 times 3. And then we would have factored this, and oh, we have got another x over here, right? And again, we're just kind of taking the long, hard way about it. Because this is not prime, I could have factored out an x, and then I would have had x minus 4, right? Because x times x is x squared minus 4 times x, which is 4x. So it would have looked like this. Would have if it would have been the problem. And that's why they were saying, because x minus 4 is the first degree, okay, it was a first degree, it's x to the first power here. And we don't really have any other, well, this is polynomials of, I'm sorry, when they read here, because x minus 4 is the first degree, its factors would have to be of 0 degree, okay? And so obviously that wouldn't, because 0 degree, we know, would create a 1, right? So ultimately, we always just have to look at our polynomials to determine what these common factors are. In this case, it was just a 6. In this case, there was a 6 and there was an x. We could have written it as 6x, but we still have to break them down into their smaller components. And in this case, we would have had more components here. So that is the end of lesson number 3.